Now that we've learned about connectedness and path connectedness and how both of those are topological invariants, in the sense that if you start with a topological space that's either connected or path connected and apply some homeomorphism to it, which is like the topological version of an isomorphism, then the resulting space will also have that property, be it connectedness or path connectedness, depending on what you started with. Now that we've seen that, we're going to see compactness, which is another topological invariant. It may be something you've seen in a real analysis course, and it's a very powerful tool, but it has a kind of unintuitive definition. You have to start with some minor preliminary definitions. For example, these two. So if you start with a topological space X, and you're given some collection of open sets in that space, and if it has the property that X is actually equal to the union of all of these subsets, these open subsets, then that collection is called an open cover of X. Okay, it's open because we're requiring all of our sets to be in the topology, meaning so all of them are actually open sets. And we say it's a cover because, well, every point in X is covered by at least one of these open sets, right? No matter what point X you pick in here, you can also say X is in one of these open sets. Okay, so that's what we have for open cover. Sometimes you'll want to talk about an open cover of a subset. So this is same word, but same term, but we use it for subsets of a space. So let's draw a picture of the distinction between the two. A whole space X has an open cover, say, maybe that's one open set. I'm not going to draw them filled in, just imagine they are. And there's some other open set, and maybe it takes infinitely many of these, but that's kind of hard to draw. But at least every point is hit, right? You cover X with those open balls. So each of those are some U sub alpha. In this case, we only needed a handful of them. So those U alphas form an open cover. But from time to time, you'll want to focus on some subset, to call it A. And in that case, we say that, maybe I'll use the highlighter for this. You are allowed to go outside the set. So let's say that's one U sub alpha, and this is another U sub alpha. Using the highlighter is nice because you can see their intersection. There's another, maybe there's a tiny one there, and one right there. I guess I should be careful not to go outside of X, but just imagine I didn't, I guess. Okay. So those 5 highlighted sets would form an open cover of A. And so the condition there is A just has to be contained in the union, maybe not equal to it. If you wanted to think about the subspace topology on A, then you could, intersect each of these open sets with A, and then you would get back to the previous definition. But it's fine to write it like this for just some subset A of your space X. But most of the time we'll be dealing with just an entire space, so no big deal. So that's what an open cover is. There's another concept called a subcover. So if you're given an open cover of a space, a subcover is just a smaller collection, right? You take that same collection, in this case, we're calling it U alpha, where alpha ranges over some index set I. And then if you just take a smaller index set, call it J, and only pick out those open sets, then you get a subcover. Right, so going back up here, maybe there were some redundant sets. Maybe that was some open set and that was some open set. Right, so then, maybe this was U1, U2, U3, U4, U5, and then this little one I just added was U6, and this little one was U7 or something. Then certainly those 7 sets cover X. They're an open cover, or sorry, they cover A. But you didn't need all of them, right? They weren't all required. For example, U7 and U6 were extraneous. I could have covered A without them because they're just subsets of other open sets that I had. So you could say something like, U alpha, where alpha is in J, is a subcover of the collection U alpha, where alpha was in I. And here J is the collection. I only needed U1, U2, U3, U4, U5. So it's just those subscripts, whereas I was the larger open cover, which went all the way up to 7. Okay, so you can take subcovers. That's the formal term for them. And you might be wondering, how is this related to compactness? If you've seen compactness in a real analysis course, you usually talk about it as a set is compact if it's closed and it's bounded. Of course, we don't have a notion of boundedness in a topological space because there's no real concept of distance. So how could you say something is large or small in a topological space? So we can't use that definition. The one we use is related to open covers and subcovers. It's kind of baffling the first time you see it, but in a topological space, you say that a subset A is compact if every open cover has a finite subcover. Okay, so what's an example of something that's compact? Well, you could try the interval from 0 to 1, making sure to make it closed. Because like I said, if you're working in the real line with the standard topology, Euclidean topology, then closed and bounded is the same as compact. So, I mean, here's a closed interval from 0 to 1. It's certainly bounded because nothing gets bigger than 1 or smaller than 0. And it's compact, but it's weird trying to argue why. You would have to show that no matter what open cover you draw, right, so this is our set, A equals this, it's a subset of R. No matter what open cover you draw, say I did, this and this, they're allowed to overlap. In fact, they'll have to. Maybe take a big one. And maybe you fit like a ton of really tiny, maybe there's some really tiny open intervals I put in here too. I'm drawing them on top and bottom just because I don't want to clutter the diagram, but you could imagine putting like infinitely many open intervals in here. Then it turns out that you can kind of just kill all the ones I added at the end, and you can get by with just finitely many. You can try to prove that if you want. It's a little bit technical, but it's good for building intuition, I suppose. How about something that's not closed? Well, let's try 0, 1 again. So it's still compact, but we'll say it's not closed, and so it won't be compact. I may have said some words wrong. Let me just repeat myself. This is an open interval. It's not closed, but it is bounded. But that won't be sufficient for compactness because you'll be able to do things like take some infinite open cover and make it impossible to get a finite subcover. So maybe you could imagine I could take some, like 1/2 to 1 or something, and then Maybe I just do that, and I get like smaller and smaller each time. And I get infinitely close to 0. I keep getting closer and closer and closer, so that in the union, I get everything. But you won't be able to take any finite subcover, because any finite cover, you'll be missing infinitely many things really, really close to 0. So maybe these intervals are of the form, oh, I don't know. I tried 1/2 to 1. I guess I'll say 1 over n to 1 over n minus 1 or something. Something like that gets close to working. You might have to fudge it a little bit. But anyway, the picture should speak for itself. You're getting arbitrarily close to 0, but never reaching it. And so you'll need infinitely many to cover. So not compact. And okay, hopefully that agrees with your real analysis knowledge that compact sets have to be closed, and this one isn't. All right, so I have that written here. Intervals of the form a comma b with both endpoints closed are compact in R, if you're endowing it with Euclidean topology. But on top of that, you can imagine taking any topological space composed of a finite number of points. So I just drew some in here. There you go, there's 11 points, I think. If I call this a topological space, it doesn't matter what the topology is, X is automatically going to be compact. Draw a box around it. It's going to be compact because, well, whatever open cover you take is going to be finite to begin with. Otherwise, you're going to be repeating stuff. I mean, how many different open sets can you pick here? You know, maybe I pick these and this, and maybe that singleton's open, and those are open. I'll pick that singleton, I'll get those two. But there's only a finite number of options you have for open sets in X. Right? Just think about the power set of X. That'll tell you how many subsets there are, and it's certainly a finite number. In this case, I guess there are 2 to the 11 subsets, minus 1 if you're excluding the empty set. And that's already finite, so any subcover of a finite set is going to be finite. So naturally compact. Furthermore, great source for counterexamples is the indiscrete topology. This time, even if you have infinitely many points, of course, I can't draw that many, but do what I can. Let's say that's our space X. And if I equip it with the indiscrete topology, remember that means the only open sets are the empty set and the whole space. And so if I took some open cover of X, well, guess what? I mean, I only have 2 choices for open sets to go in my open cover. The empty set doesn't do anything for me. So an open cover of X, I'll just say this is an open cover of X. And really, it's the only open cover of X. Right? Like I said, you could toss the empty set in there as well, but it's not going to change anything. And so that's already finite. So take a finite take a subcover and it will be finite as well. So great source for counterexamples to, or just examples in general. Discrete topology then, so if everything is open, tau is the power set of X, so every subset is an open set. And just to make things nice, let's suppose X has infinitely many elements in it. Then X cannot be compact. Why is that? Well, again, I can't draw infinitely many points. Just use your imagination. But that's your space X, and it has the discrete topology, then in particular, we know every singleton is an open set. And so I can build an open cover, say, maybe call it curly U for the collection of open sets I'm going to build. Just make it the collection of all singletons, such that X is in our space X. So this collection ranges over all possible choices of X, builds a singleton around it, and then as it fills out the whole space, guess what? That's an infinite open cover because X has infinitely many points. And if you toss out any one of these, say I tried to make a subcover, even tossing out one ruins it for me, right? Then I'm no longer covering that point. So there are no finite subcovers for this particular open cover. And so the space is not compact, right? Remember the definition of compactness said every open cover must have a finite subcover. So to show it's not compact, you just need to exhibit one open cover where it fails. And that's what we just did. Side comment, it's always possible to find an a finite open cover of any topological space. Namely, do this kind of trick. The whole space is always open. You can make a trivial open cover with just one open set, namely the space itself. But that's just kind of a parlor trick. For compactness, you need to show every open cover has a finite subcover. And in that case, this open cover does not have any. So there you go. There are a lot more examples you can give. Some of them get fairly ugly. Most of the examples you'll encounter in day-to-day life are of this form. If you're working in Euclidean space, even if you're in higher dimensions, that characterization is formalized by what's called the Heine-Borel Theorem, that a subset of n-dimensional Euclidean space is compact if and only if it's closed and bounded. So that's a pretty powerful statement. It's an if and only if, which means if you know it's compact, you can automatically say it's closed and bounded, and vice versa. If you can prove a set in Rn is closed and bounded, that tells you it's compact. And there are lots of proofs for this. It's fairly technical and not super enlightening in my opinion. So we'll take this one for granted. It's just a good one to remember that compact implies closed and bounded and vice versa if you're in Euclidean space. And there are some other nice theorems you can prove about compactness. Namely, a Cartesian product of topological spaces is compact if and only if each one of its components is compact. Right? And hopefully that's not, again, it's a little challenging to prove, but hopefully it's not surprising in the sense that, yeah, if I start with some compact space X and I cross it with some compact space Y, then their Cartesian product looks like it should be compact. Of course, the drawings I'm doing are based on your Euclidean brain, and you're thinking, okay, compact means closed and bounded, so I drew closed sets that are bounded in their size. But it works in general in topological spaces that aren't just Euclidean space. And vice versa, if you take some compact Cartesian product, that means each of the components will be compact. Sort of if you project onto each of the axes, those will be compact as well. Okay, so that one we won't prove because it's a little tedious, but we can prove some really interesting things. For example, if you have a compact topological space, then any closed subset of it will automatically be compact. And keep in mind here, we're thinking topologically, so closed means its complement is open. We're not thinking in terms of limit points or anything, we're thinking topologically. So it works in Euclidean space as well. So yeah, a closed subset of a compact space is compact. This one is fairly quick to prove. And I have a few other theorems that are in similar veins. A compact subset of Hausdorff space is closed. Continuous image of a compact space is compact. That should ring a bell because we did something similar for connected sets. And then we'll talk about this one later, but there's a way to guarantee when a function's a homeomorphism based on some interesting properties. And all of these are things I'm going to prove right now. And they're all things that any aspiring topologist should pretty much be able to prove in their sleep, which isn't to say they're easy. There are some tricks involved that are kind of difficult to follow the first time you see them. Rather, I just mean that these tricks are going to come up again and again, and they're going to be incredibly useful things to know. So if you really like topology, these are good tactics to just keep in the front of your brain if you ever need them, which you likely will. So a closed subset of compact is compact. Well, let's start with some notation. Let's say let x comma tau be a compact space. And let's pick some closed subset. Call it A, maybe. So A is a closed subset of a compact space. My goal is to show A is compact. And from our definition of compact, we know that means that every open cover has to have a finite subcover. So the very first thing I'll do is I'll say let this be some open cover of A. And let's get a picture brewing just so we have something to look at. The goal here, X is a compact space. A is, actually, let's draw it in one dimension maybe. Let's say this is X. And A is some closed subset of it. Right, so again, in your brain, you're thinking probably in a Euclidean way, but this will work in general. That if we do have some setup like this, then what can we do? Well, we want an open cover of A. So remember, an open cover might spill out into the surrounding space. So I might, have this set, and I might have this set. Maybe there's a tiny one here. Let's actually draw this differently. I'll draw them above so they're not really overlapping. So there's that. Let's say that. Okay. Something like that is my open cover. So these are my use of alphas. So I have an open cover of A. Perhaps there are infinitely many of these. Again, I just can't draw that many. And now our goal is to prove that I can find some finite subcover. Okay, well, what can I do? That's fairly difficult, right? If you're just thinking about A and its open cover, well, no idea what to do. I don't know what those sets are. I don't really know anything about A. Or wait, I do. I know A is a closed set. And I said closed means complement is open. Okay, so I could think here, oh, its complement is, that chunk plus this chunk. So that's, just erase this, that's A complement right there, or X minus A if you want to think about it that way. And that's another open set. So what happens if I just add that to my collection? So I started with my red sets U sub alpha, where again, I drew only 5 of them, but there could have been infinitely many. And now I'm tacking on A complement, which is an open set. And I can say that that is an open cover. And hopefully you see it by now, that's an open cover of X. But what do we know about X? We know X is compact. Right? There we go. X is a compact topological space. And let's actually write that out. Since X is compact, there exists a finite subcover. A finite subcover of this thing we just wrote out. Okay, now what could that finite subcover be? Maybe it's just a finite collection of these, and it, well, let me phrase it this way. We're going to need this more than likely. More than likely, we're going to need A complement because, I mean, I said these were spilling out maybe, but they might not spill out far enough to cover all of X. So in general, you're probably going to need this. So when you take your finite subcover of everything, that's going to mean the U alphas have to be a finite collection as well. So I'll just say hence. Actually, let's give it a name. So there exists a finite subcover, say U alpha sub I, and let I range from 1 to n. And let's just, for safety's sake, toss in A complement, that secondary open set we found. Then what happens? Well, it turns out that this collection, ignoring the A complement, ends up being a finite subcover of the cover we started with. So let's write that down. This is a finite subcover of the original cover of A. And since that original cover was arbitrary, I did effectively show it for every open cover. So we're saying every open cover of A has a finite subcover, therefore A is compact. Okay, and when you think about this proof in your brain, you don't have to go into as much detail as that. In fact, well, you could actually go into more detail. You could be super precise, and maybe you want the subset to have the subspace topology, and you would have to define what that means and do intersections and all that stuff. But if we're just talking about a subset, then compactness is fairly quick. You just say, take an arbitrary open cover of your set. The complement is another open cover. That gives me a cover of my entire space X. But X is compact, so that restricts to a finite cover, and that finite cover will cover A as well. And there you go. So closed subsets of compact spaces are compact. What else could we see? Compact subset of a Hausdorff space is closed. This one takes a little bit of work, and it helps if you draw a big diagram for it. So let me just start with a diagram. Let's say I have some space X, and X is going to be Hausdorff. And I want to take some compact set in X. Maybe I'll draw that like so. A little Tetris block or something. There's A. A is going to be my compact set. So let's start writing this down. Always name your topological space. Hausdorff. And we're going to say A is a compact subset. Then I want to show it's closed. Showing closed in a topological space is, it's possible to do it directly. It's often easier to show that the complement is open. That's how we defined closed to begin with. So really, we want to think about a complement existing out here. And hopefully, the fact that A is compact will mean a complement is an open set. So let's think about how we might prove that. If I want to show something's an open set, well, again, you might think that's kind of difficult. You might think, well, open just means it belongs to the topology. And what do I know about the topology? Not really anything besides the fact that it's Hausdorff. But there's another way to prove things are open. Namely, you can prove, just erasing this boundary. You can prove a set is open by doing it pointwise. You could take an arbitrary point, in this case, let's call it X. So X is in the complement. The complement's the thing I'm trying to prove is open. And if I can prove that a complement is actually a union of open sets, then a complement itself must be open. So that's going to be my goal. My goal is going to be put some open set around X. That open set, maybe we'll call it U, will exist completely within a complement. And that would mean X is an interior point, so a complement's equal to its own interior, and the only time that happens is if you're an open set. Okay, so how can we do this? Again, our goal is to let, or to show that a complement is open, so we'll say let X be in a complement. Then what can we do? Well, again, whenever you're stumped, just think, okay, there's some stuff I've written down, it's not gotten me anywhere, but I have some assumptions that I haven't used yet. In this case, I know my space is Hausdorff. Meaning, if I pick any point distinct from X, then I can put open sets around each of them, those open sets being distinct. So for example, I could take this Y, put an open set around it, call it V maybe. And since my space is Hausdorff, I know those open sets will be disjoint. Okay, so let's be more precise here. Let's actually write this out. I'm just going to zoom in and erase the bits here. Oops. Erase all of that. Okay, so let X be in the complement. And I'll say for each Y in my set A, let I'm going to call them u sub y and v sub y instead of u and v, because they're really depending on y, right? I'm going to do this process for each point y in my subset. So let these be open sets such that the Hausdorff conditions are satisfied. Namely, okay, x is in the first one, y is in the second open set, and the intersection of these open sets is empty. And I'll just make a note here that's possible by the Hausdorff condition. And let's draw those again, because this time I want to be more careful. Hausdorff doesn't tell me anything about how nice these sets are. Initially, I drew them like this, as nice as they could possibly be. But in reality, they might have been hideous. You know, maybe this was the open set that the Hausdorff condition picked. And, you know, this was the open set picked for y. So that's Vy, that's Uy. Of course, they're disjoint, but that's basically all I know. So in that worst case scenario, I need to do more work, right? My goal was to find an open set fully contained, like outside of the yellow Tetris block, but I haven't done that yet. So how could I do it? Well, I said we were going to do this for each y. Right, so next, you know, maybe now this is my y, and maybe I pick this open set. That's my new Vy. Maybe I'll call this y2 or something. And similarly, I get some u sub y2 around x. Maybe it's hideous, but at least it won't intersect the other teal set. And I keep doing this, right? I keep iterating, and for every single point in my Tetris block A, I get some pair of disjoint open sets. Now, what you might think to do if you keep drawing these is you might think, ooh, the way I could get around this is by, or the way I could get around the fact that like these sets actually bleed into the set A, is you might think, what if I take intersections of them? Right? Intersections will make the set smaller, and so the intersection of those two sets would be like this. And now it's just bleeding in a little. But then, you know, eventually I would pick some y here, and whatever open set around x I draw can't contain y, right? So maybe eventually, after I do that enough, I'll whittle this down until it's actually outside of your set A. So that's going to be our goal, and let's just work through the logic and see if it pans out. What we'll do first is I'll say note that the idea wouldn't work if I was doing that infinitely many times. And it's entirely possible there are infinitely many points in my set A. Right here, I've just drawn 2 of them, but maybe there are infinitely many. I mean, more than likely there will be. But what do we know about A? We know that A is compact. So compactness is the thing that lets you take something that's infinite and reduce it to something that's finite. So even if there are infinitely many points in Y, I should be able to do something finite with them. So let's write this out. Note that the collection of all these V sub Ys, where V is the open set around Y. I'm letting this Y value range over every point in A. Note that that's an open cover for A. Why? Well, it's hitting every point, right? So it's definitely gonna It's definitely going to hit all the points y. Maybe it even bleeds over some, but who cares? It'll be an open cover. Since A is compact, there exists a finite subcover. And let's say there are n elements in the subcover. And so we'll start denoting things v sub y sub I, so like that y sub 2 there. Right, I can do that because there are finitely many now. So that's our finite subcover of the set A. Now, what does that matter? I mean, the sets we were really concerned with weren't the v sub y's, but the u sub y's. Right? We wanted these little eggplant shapes. And those are completely unrelated, right? Well, no, they're exactly related, right? For each of those Hausdorff conditions, we got a pair. So instead of thinking about the collection VYI, I could think of the collection of U sub Y sub I. And in particular, we're going to do that intersection trick that I mentioned. Define U to be the intersection. And this time, I don't have to worry about taking an infinite intersection of open sets. Instead, I'm just going to intersect finitely many open sets together. And we know from the definition of a topology that intersecting finitely many open sets together is fine. And that'll still be an open set. Right, so this set U, which I've defined as a finite intersection, is in my topology. It's an open set. And the hope is that it'll be some small set totally disjoint from A, fully contained in A's complement. Maybe I'll hide this tau bit for the second. Observe that X is an element of U. Why? Well, it's because X was an element of U sub yi for all of those sets. Right? That just comes from right here. X is always in U sub y, so it's going to be in their intersection. Observe that X is in, or sorry, U is in tau. U is an open set. And we said Y, it's a finite intersection of open sets. And most importantly, U intersect A is empty. Okay, and that's the goal that I've been drawing up here all along. You wanted some set U that didn't touch A, because that means U is fully contained in A complement, meaning it's an interior point of the complement, meaning the complement is an open set. Okay. Now, why is that true? Well, you can prove it by contradiction. So what would we have otherwise? Otherwise, we would have, I've already used X and Y, so let's use Z. Otherwise, there would be some point in their intersection. But what does that imply? Well, if Z is in A, let's start with U. If Z is in U, well, that's the definition of U. That means Z is in U sub Y sub I for all n of those sets. So Z being in U implies that. What about Z being in the set A? Well, what was What was the defining characteristic of A? Well, I didn't write it explicitly, but we had some interesting property here that we already had an open cover of A. So let's actually write out what that means. This means that A is contained in the union of V sub y's. And in fact, you could say that for the subcover as well. So let's write this down here. A is contained in this union because it's a subcover. And so if Z is in A and A is in the union, that means Z is in this union. But what does it mean to be in a union? Well, it means you're in at least one of the sets composing that union. So written down here, I'll say and Z is in U sub Y, let's use a different index J. That's for some J in those finite collection. Okay, and hopefully you see a contradiction here. Z is in U sub J, or U sub Y sub J. And Z is also in, did I write this wrong? That was supposed to be a V, wasn't it? One of these was supposed to be a V. Yeah, that's supposed to be a V. My mistake. Now you hopefully see the contradiction. Z is in VYJ, but it's also in UYJ. In particular, because J is one of these guys. So this implies Z is in both UYJ and VYJ, but lo and behold, Hausdorff kicks in and says that's not possible. The intersection between that pair was guaranteed to be empty. I picked those sets to be disjoint. So that's a contradiction. Let's do a little lightning bolt for contradiction. Meaning, yeah, this has to be true. What do we have? U is an open neighborhood of X, and U is fully contained in A complement. That's the exact same thing as saying, well, if U doesn't intersect A, it must turn out that every point of U is in the complement of A. So X, say X is in the interior of A complement, but X was an arbitrary point of A complement. Therefore, that actually tells you A complement is equal to its interior, which is the same as saying A complement is open. But if the complement of a set is open, then that set is closed. And that's where we wanted to get to. A compact subset of the Hausdorff space is closed. You can see why I left a whole page for this proof. It did take everything. So again, I said these are important proofs that every topologist should be able to prove in their sleep. It doesn't mean they're easy. It means these techniques are vastly important, and you should be able to apply them once you've gotten used to them. Right? It's really important that if you're trying to prove a set is closed, you think, ooh, what if I prove its complement is open? And then, oh, how do I prove something's open? Well, I show that every point's interior to it, right? Because that would mean that set is equal to its interior, but the interior is open, right? So the set has to be open. So you have to think, okay, I take an arbitrary point X and I try to fit an open set around it. How do I do that? Well, Hausdorff gives me open sets. But maybe it gave me infinitely many because there were infinitely many points Y. But oh, I have compactness. So that whittles it down from an infinite collection of open sets to a finite collection. And what do I know about a finite collection of open sets? I know their intersection's open. And there you go. Right? They're all very important concepts in topology. And I think this proof is kind of beautiful that it uses all of them and in such a nice way. Right? This all fits together pretty well once you understand the notation. Right? The notation's kind of hideous, and this drawing wasn't that great either, but there you go. Okay, so we have two tools so far. We know if you start with a compact space, any closed subset will be compact. And if you start with a Hausdorff space, any compact subset will be closed. What else can we do? We can take a continuous image of a compact space and show that it must be compact. How would we do that? Again, this should ring bells for connectedness, the fact that the image of a connected set is connected. Well, let's see. Continuous image of a compact space is compact. So again, pictorially, we're thinking I have some space X, it's compact, so I'm using my Euclidean brain to draw it as a closed and bounded set. I have some function Y, or some function F being applied to give me something. So the image of X is apparently supposed to be compact as well. To verify that, let's draw that a little bigger, actually. Okay, so F goes from the set X to its image, and we're assuming this set on the left is compact. How would I prove that this set on the right is compact? Well, again, we only have one definition of compactness, and that depends on some arbitrary open cover having a finite subcover. Okay, so let's start as usual. Let's say we have some compact topological space. And we'll assume F is continuous. So we'll say F from X to its image. Maybe this is bad notation, who cares? Is continuous. Let that be continuous, I should say. And we want to take some arbitrary open cover. So let U sub alpha be some open cover of F of X. All right, if I want it to be open, I guess I need to say that there's some topology on the codomain. So maybe I will be more precise here. Yeah, let's be more precise with it. So let's call our codomain Y with the topology tau prime. I don't know anything about it. And let's just say F goes from X to Y. Just to be more general. That's a continuous function. Okay, so that handles notation. Now I want to say I'm going to use V here. Sometimes I like to use V's if you're working in the codomain. So let's call it V sub alpha. Be a collection of open sets in the codomain. And we're going to let that be an open cover of the image of X. We're trying to take an image of a compact space. X is that compact space. So we're considering an open cover of the image of X. So fixing this up, that's why. if F is surjective, then the image is all of Y, but maybe F only lands here or something. So maybe that's the image. Who knows? We're being as general as possible. Okay, so I have an open cover of this little space. Let's change this purple. I think I've been drawing my open sets in red, so let's continue doing that. So let's imagine, I have some sets here. Again, I'm going to draw them kind of overlapping in this weird way. Right, so there's my open cover, V sub alpha. And what can I do? Again, we've gotten as far as we can with definitions. Now we have to use some of our assumptions. What do we know? We know our function's continuous. And continuous to a topologist means the preimage of every open set is open. And lo and behold, we have a bunch of open sets in the codomain. Why not pull them back to the domain? So I'll say, since F is continuous, preimage of V sub alpha is open. And that's true for all alpha, whatever your index set is for that open cover. Cool. So I've pulled these back now, and maybe they warp shape a little bit. Who knows, maybe some of the short ones got long and the long ones got short. But the way I'm drawing this, the implication is hopefully that they'll still cover X. If that didn't happen, I'd be at a loss. But it will. So let's say this. Let's define U alpha to be the preimage of V alpha. Then this collection, these pullbacks, I could call them, well, they have to be open, because preimage of open is open. That's what we just said. So they're in tau. And I'll say it's an open cover of X. This one I'll leave as an exercise. It's short, it's just some set theory, but proving that it's an open cover means you should actually sit down and verify X is the union of all these U alphas. And really, to do that, you only have to show subset in one direction, namely this direction. So you should pick an arbitrary point in X and show it has to be in that union. So I'll leave that for you to do. Okay, so we have an open cover of X. What do we know about X? X is compact. And so any open cover becomes a finite subcover. And again, I'll just write it something like U sub alpha sub I. We'll say there are n sets, n being some positive integer. Okay, great. So I have some finite subcover. Am I done? So I've taken these U sub alphas. I've knocked some of them out, so there are only finitely many left. But no, I'm not done. What I have to do, I was supposed to find a finite subcover of the V sub alphas. Okay, so what do you want to do with this? The temptation is to say, well, I have these sets U sub alpha. I want to maybe push them forward. Right? Apply F to each of them, and then there we go. But what you get might not be a subcover of this original cover V sub alpha. right? We would have to know something about like injectivity or surjectivity. I forget which, probably injectivity, to prove that. Because, for example, if you took the image of u sub alpha, that would be the same as the image of, well, what is u sub alpha? It's this. It's the pre-image of v sub alpha. And like, you want this to be equal to v sub alpha, but that's only true with some additional conditions on the function f, and we don't have those conditions. So instead, what's the best you can do? The best you can do is say that forget about pushing them forward. We have some finite index set, I ranging from 1 to n, and we have a sort of one-to-one correspondence between u alphas and v alphas. So why not just consider the collection of v alpha I is ranging over the exact same index set. And then this ends up being a finite subcover of the original subcover, which was just all of the v sub alphas. Again, that requires proof. Right? You should sit down and verify, okay, it's certainly finite, right? It goes from 1 to n, there's nothing to prove there. It's, this is certainly a sub collection of this, so nothing to prove there. But proving it's a cover, again, takes a little bit of set theory knowledge, but not terribly much, right? It comes directly from the fact that we had a finite subcover here. So sit down and prove that if you like. Therefore, what does that imply? That implies f of x, the image of the domain, is compact. Because I started with some arbitrary cover, open cover, and proved it had a finite subcover. And again, this one's a bit wordy, but when you sit down and think of it, all you're saying is take some open cover of the image, pull it back to a compact space. Since that space is compact, you can throw out a bunch of those, just retain finitely many open sets, which are still covering x. And since they're still covering x, their corresponding finite subcollection in the codomain still covers the image of x. Cool. So what else do we have? We have the sort of coup de grace of any chapter on compactness in a topology textbook. That if you have a compact topological space and a Hausdorff topological space, where x is going to function as our domain, y as our codomain, and we're given some function between them that happens to be continuous and bijective, then f is a homeomorphism. Okay, kind of a mouthful. Let's remind ourselves, homeomorphism means 3 things. 1, it means bijective. 2, it means continuous. And 3, it means its inverse is also continuous. We're actually given 2 of these, right? We're told it's continuous and bijective. So the only thing remaining to check is the inverse of f continuous? And apparently all it takes is for your domain to be compact and your codomain to be Hausdorff. Then any function like this will have a continuous inverse. Weird. How do we show it? It's really slick, actually. It's slick because we can use the 3 proofs we just laid down previously. And so first I'm going to say one thing. Recall that f being continuous is the exact same as saying the preimage of every open set is open. But, and this is another good mini exercise for anyone studying topology to sit down and prove, you could phrase it exactly as well by saying the preimage of every closed set is closed. So if you haven't seen that proved before, go off and try to prove it. It's not too difficult, it's a few lines. So let's recall that. And so I'm going to be trying to prove that F inverse is continuous, and I'm going to use this characterization of continuity. So let's write it like that. Let's just, instead of writing F inverse, let's call it G for the time being, just so I don't get confused between preimage and inverse and all of that. So let G from Y to X be the inverse function of F. And I want to say the preimage of any open set or any closed set is closed. So I'll say let A subset of X be closed. Right, you're thinking backwards. The inverse is going in the reverse direction. So you're taking something from X, and then a preimage under the inverse will give me something in Y. A little backwards. But if you're okay with that little bump, the rest of it's beautiful. What do we know about closed sets in compact spaces? Right? A is a closed subset of a compact space. Oh, well, we think back to that proof, right? Where if I had a closed set, I could take its complement and it's open, and then bring it back down, and any open cover would have had a finite subcover. So A being closed implies that A is compact. Closed subset of a compact space is compact. But what else do I know? I know that the continuous image of a compact set is compact, right? So I could say, well, A is existing in X, and I could think to myself, well, F is a continuous function, so that means F of A, the image of A, has to be compact. But now what? Well, F of A was in X, right? F sends things in X to things in Y. So F of A is in Y, and Y is Hausdorff. What do I know about compact subsets of Hausdorff spaces? Well, they're closed. And what else do I know? I know that that the preimage of A is closed. And that's exactly what we wanted. Took an arbitrary closed set, showed that its preimage was closed. So kind of bringing together all these results to show something really nice in that anytime you're working with a compact domain and a Hausdorff codomain, you really only need to check two things. If you check that your function is bijective and continuous, then this piece falls into place immediately. It comes in handy more often than you would think, other than being a really elegant proof uniting a lot of important results. It is useful. Anyway, that's it for compactness. That effectively shows us that compactness is a topological property. It's preserved by homeomorphisms. And so if you had two topological spaces, one of which was compact and one of which was not, there you go. That's all you need to show they're not homeomorphic. I mean, for that reason, you know, the real line is not homeomorphic to some closed bounded interval. Not homeomorphic because this guy is compact, this guy is not, assuming the Euclidean topology. Anyway, comes in handy a lot of the time, just like connectedness. And that concludes our discussion. Thanks for watching.